So we are learning about the M-type tubes or closed field tubes. Earlier we have learned about the klystron, reflex klystron, which is falling under the category of linear beam tubes or O-type tubes. There we can see that the magnetic field is parallel to the electric field. So the purpose of magnetic field here is just to focus the electrons which is coming out of the cathode. Cathode to anode, the trajectory of the electrons, they should not be spreading. So the magnetic field is just helping to focus the electrons from cathode to anode. But whereas in the case of crossed field tubes, we can see that the magnetic field is perpendicular to DC electric field. That means the magnetic field is having a particular role in these kinds of devices. Now we know that the magnetic field is always creating a curved path. So the movement of electrons will be also in a curved path in the case of crossed field tubes. And they are also called as M-type tubes. And there are a number of cross field tubes, and for us we need to know only the case of magnetron. And there are different kinds of magnetron, and the magnetron was first invented by Hull. It was just a laboratory experiment, and in the World War II, there was an urgent need of an oscillator or a RF signal or a high power microwave generator, and that is the time when there was a rapid development for the magnetrons. And there are different kinds of magnetron oscillators. The negative resistance magnetron or split anode, then comes a cyclotron, a frequency magnetron, cavity or traveling wave magnetron. These are the so-called as simple magnetrons. And out of that we are going to be learning about the cylindrical magnetron, which is of cylindrical shape. And it is also called as the cavity magnetron. So if you look into their structure, we can see that it is having a cylindrical shape first of all. And in the center we are having the cathode. The center we are having a cathode with a radius A. The cathode is having a radius A. So this is made as the cathode because of the potential or because of the DC bias V0, which is called as the beam voltage or the electron beam voltage. The electron beam voltage negative potential is given to the cathode, and the positive potential of that is given to the section which is going to be acting as the anode region. And you can see that anode is not simple, it is not a simple structure. The anode is split into so many slots or holes, and all these slots are going to be acting as the resonant cavities. So what are resonant cavities? These are cavities which is going to be creating a resonant frequency. So the construction is simple. We are having a center cathode which is connected to negative of the beam voltage, the positive anode, the anode which is connected to the positive of V0, and the anode is split into so many slots, and each of the slots is going to be acting as a resonant cavity. And the magnetrons are basically oscillators. They are oscillators means what? They are going to be producing a sinusoidal signal, or they are going to be producing oscillation. Now, how are they producing oscillation? Without anything, they cannot produce. So, the oscillation, the trigger point for any kind of oscillation is nothing but the noise. So, the noises are present in which position? It is present in the resonant cavity. And we can design the magnetrons in such a way that we can have a number of cavities and we can have different shapes. So it is all depending upon the type of application that we need. So this is a simple construction, 2D view of the cavity magnetron in the top side. So in the top side view, the center is the cathode with a radius A. We are having the anode. Here it is showing an 8 cavity because you are having 8 cavities in the anode. Cathode is connected to negative V0, anode is connected to positive V0. V0 is capital V0, which is the electron beam voltage. And since this is an oscillator, we are going to be taking output, and to one of the cavity we are going to be connecting the output RF session. And we are giving, see that here we are giving a magnetic field. In the earlier figure also, we are having a magnetic field B0, which is applied in the Z direction. So here it is shown as plus B0, which is applied in the Z direction, and the space between the cathode and the anode, which is having a radius B, it is known as the interaction space. It is where the electrons are being interacting. Now, in order to know how these cavities are going to be acting as resonant cavity, we know that resonant cavity or the resonant cavity is going to be giving a frequency f is equal to, practically it's going to be giving a frequency of 1 by 2 pi root LC, but we don't have the concept of L and C in the case of microwaves. So here the current carrying the section of the cavity is going to be acting as the inductor section, and this charge varying this space is going to be acting as the capacitance, giving an LC effect. So that is how each of these cavities are going to be acting as resonant. So this is what is depicted here. The current carrying conductor is going to be giving you inductance, and the charge variation in these two places is going to be giving you the capacitance effect. And the working principle, we can depict it in two ways. That is, in the presence of RF field inside the inside the cavity, and in the presence of RF field. So initially, this we don't have any kind of noise. The first thing is this, we are not taking any kind of noise or any kind of RF signal is present in these anode cavities. So what will happen is, when we are giving a bias, which is V0, that is the cathode as well as anode is activated. So when we are giving this bias, the electrons from the cathode, they are going to be moving out with a velocity is equal to root of 2e capital V0 by n. Now, how did we get is this? We know that the energy of electron, because of the applied voltage, is E into V0. V0 is our applied bias, which should be equal to the kinetic energy of electrons. That is half into m into V square. Kinetic energy is half m V square. So this capital V0 is indicating the DC bias, and small letter V0 is indicating the velocity. So from this, what should be the small letter V0? We can say that it is equal to 2, taking 2 to the other side, 2 into E into capital V0 divided by m is equal to what? Small letter V0 square, or what is our velocity V0? V0 will be equal to root of 2e V0 by m. So the electrons which are coming out of the cathode, it is coming with a uniform velocity root of 2e V0 by m. And what will happen is, the first trajectory, we are taking the first trajectory, which is A. That means in this trajectory there is no bending, which means that there is no magnetic field. See that whenever there is a magnetic field, there should be some kind of a bending. So A is indicating that there is no bending or there is no magnetic field. Or we can say that the B0 is equal to, or the B0 is equal to 0 in the case of the A trajectory. Now the second trajectory is B, which is indicating a small bending or a small curve path. So which is denoting there is a small magnetic field which is being applied. So that is the second case. The third is, we can see that the electrons are just touching the anode and they are coming back. In this case, we have applied a little bit more higher magnetic field, and that magnetic field we call it as the B0C, which is called as the Hull critical magnetic field or the cutoff magnetic field. Critical magnetic field or Hull critical magnetic field or the cutoff magnetic field. And the last one is the trajectory D, which is showing a more bending. That means the magnetic field is going to be very higher in this path. And this is not recommended because the electrons which are moving out of the cathode with a higher velocity, when they are coming back again to the cathode, it is going to be destroying the device. So D is not a welcomed. Now what will happen is, the simple cases when we are going to be giving the B0 bias, that is the anode cathode bias, electrons are going to be coming out from the cathode. They are trying to reach the anode, because electrons always try to attract the opposite. So electrons are going to be attracted towards the positive anode. And in the A trajectory, there is no magnetic field applied. In the B trajectory, we have applied a small amount of magnetic field B0. In the C trajectory, the electrons are just touching the anode and they are coming back, and that particular magnetic field is called as the critical magnetic field or Hull cutoff magnetic field. And D is a trajectory in which we have applied a magnetic field greater than the Hull critical magnetic field. There their electrons cannot even touch the anode. Before that itself they are coming back to the cathode. Now moving on to the next one, that is our main case, that is in the presence of RF field. So in the earlier figure we didn't show anything in the resonant cavity. In this figure we can see that we have drawn a number of electric lines in it, which means that in each of these cavities you are going to be having the presence of a sorry, the presence of a RF signal or a noise signal. So the noise signal is maintained in such a way that it is 180-degree phase shifted. You can see that here it is represented as minus, here it is plus. And likewise, adjacent cavities are plus or minus correspondingly. That means each of these cavities are going to be having a phase shift of 180-degree. So that is why we say this kind of oscillation as pi mode of oscillation, or it is the dominant mode in the case of 8 cavity. And we can see that 180 means what? Here if the noise signal is like this, in the adjacent cavity it will be just the reverse, 180-degree phase shifted signal. And we know that from the figure itself it is clear that the noises are not present entirely onto the cavity. Some of the noise are fringing out, they are coming out and they are spreading onto the interaction space. See the interaction space. So we always see that the electric lines are always from plus to minus. That is what is drawn here, plus to minus. The arrow, please indicate, please see the diagram also. Always electric field lines will be from plus to minus. Now we are going to be moving on to the detailed working. So remember the path of electrons. Now imagine an electron A. Imagine an electron A. It is going to be coming out of the cathode with a velocity V0 is equal to root of 2e V0 by m. They are coming with a higher energy, and this electron A is going to be hitting, or they are going to be interacting with the negative going phase or the retarding phase of this cavity, of the noise in this cavity. That is, in this cavity, the negative phase, the retarding phase, the electron A is going to be coming and hitting. So what will happen? There will be an energy transfer between A and this, because this is having what? Lower energy, and this electron is having what? Higher energy. So energy transfer will be always from what? Higher energy to lower energy. So what will happen now? This electron A is transferring their energy to this noise. So this noise signal is going to be boosted. Now what will happen to A? A is going to be moving with a reduced velocity. So it is going to be what? It is going to be attracted, or it is going to be again under the magnetic field. So they cannot reach the anode at once because their energy is being reduced. So this A is again being present in the interaction space itself. And this A electron, it is again moving to the next cavity. There also it is going to be hitting with the negative going cycle of this noise, thereby transferring again its energy, and likewise their trajectory is again increased in the interaction space because they cannot reach the anode at once because they don't have higher energy. They are being under the more pressure of the magnetic field. Again this A is going to be moving on to the next cavity. There also they are hitting with the retarding phase, and at a particular point they come into a situation where they can reach the anode. That is, their final destination is being reached. That is, we can see that A is the electron which is going to be transferring their energy in their journey, in their trajectory. This A is a person which is going to be hitting all the retarding phases. They are going to be transferring maximum of their energy, and then they are reaching their destination, which is the anode. So such kind of electrons we call it as the favored electron. So that is what we need, because the concept of oscillation is we are going to be giving energy to the noise signals which is present in the cavities to make it a sustained oscillation or a strengthened oscillation. So A is the one which is going to be giving energy to this signals. Now imagine another electron which is going to be coming out of the cathode, and it is hitting the positive cycle of the noise which is present in the cavity. So what will happen? These electrons are going to be again gaining the energy. So when they are gaining energy, what will happen? They will be again returning back. They will be having higher energy and they are going to be returning back to the cathode. Such kind of electrons are coming as B, and these are called as the unfavored electron because they are not transferring the energy to the noise signal. Instead, they are taking energy from the noise. So such kind of electrons are called as the unfavored electrons. Now the favored electrons are the ones which is following the trajectory of A, and we can see that D is a person which have followed the path of A in an earlier phase, and C is another electron which have followed the same path of A at a later stage. And we can say that all these favored electrons, they will be moving in the, or they will be collected in the form of bunches, and they will be moving in the form of spokes of a wheel. So likewise, and this effect is called as the phase focusing effect. This is the phase focusing effect. That means all the favored electrons which are going to be coming in a synchronization, or they are going to be forming bunches, and they are transferring their energy to the RF signal. That concept is called as the phase focusing effect. B is the electron which is going to be hitting the positive phase, and they are going to be again backheating, or they are going to be again coming back to the cathode without giving any energy to the RF signals. So such kind of electrons are called as the unfavored electrons. And this is for a dominant mode. The adjacent poles that is already mentioned should be having pi mode of oscillation. So the relative phase of the individual cavity is given by the equation QV is equal to 2 pi n by capital N. Capital N is nothing but the number of cavities. Here in the case it is 8. N is nothing but an integer which is having the values n is equal to 0, plus or minus 1, 2, likewise. So if pi mode means what? If the value of n is equal to capital N by 2. When we are substituting that, we get what? 2 pi. Instead of n, we are going to be giving n by 2 divided by again n. So we get it as what? Pi. So pi mode is a condition in which the value of n is equal to n by 2.